I'm going to talk about a geometric representation of vectors. So we talked a little bit about this way back in AP Prep, but we didn't do a whole lot with it. And so you may or may not remember that. If you are in physics or have had physics, a lot of this hopefully will look familiar. If you haven't had physics, then you're going to have a little steeper learning curve. I think this is a little bit tricky to kind of wrap your head around, especially in the beginning. So make sure you ask questions. So vectors are also known as directed line segments, and I've drawn a few of them here to the right. You see the blue vector U, the red vector W, and the white vector V. They are used to measure quantities that have both a direction and a magnitude. So in real life application, that lends itself well to talking about things like force, velocity, acceleration, momentum, torque. Those are all familiar terms if you are a physics student, but maybe a bit of a head scratcher if you haven't been there. Now, a lot of the language and actually the math that we do with vectors exactly parallels or overlaps what we've been talking about with polar coordinates or the polar form of complex numbers. So in particular, if we say the magnitude, this looks like, I'm going to call that a U. So this, which some books will use, and some will use the double bar, they're interchangeable. So this is referred to as either the magnitude of the vector U, or it can also be read as the absolute value of that vector. Just struggling to spell value here. And that will be represented by its length. So we tried to draw this to show different magnitudes. So when you look at the red vector W compared to the blue vector U, since the red vector is longer, we would expect its magnitude or absolute value to be greater than that of the blue vector U. Now, two vectors are equal to each other if they have the same direction and the same magnitude. So same length, same direction. So you may have to use your imagination, but my intention was to make U and V equal to each other, but clearly U and W are not equal to each other because they have different direction as well as different length. So this is the language and symbolism we're going to try to use with vectors. Then we rename what we have talked about all the way up till now. These ordinary numbers we now refer to as scalars. And they are used in applications like things that have only that one dimension: speed, time, distance, so on, things that we have a little bit more experience with than we do these other things like force and velocity and acceleration. So let's look at the geometric meaning of addition of vectors and then subtraction of vectors. So what we do when we add vectors is we will use the reference tip to tail. So we can show it visually. And one thing that's important here with vectors is these are slidable. So whatever we have drawn, wherever we've drawn them, on my iPad here or on the paper, you can think of them as being, you can move them around. And as long as they stay the same length and they stay pointed in the same direction, then that's a legal move there. So to show what the vector, I'm going to call this a red one. So what the vector A plus B looks like is we're going to slide this B vector and put, this is the tip of the vector where that arrow is, and this is what I mean by the tail, that initial point, that thing where it starts. So if I slide that B up so that it is tip to tail with the vector A, then if I look at going from the tip of A, or from the tail of A to the tip of B, this red vector is what we call that a plus b vector, which is referred to as the resultant. So when you add two vectors, you get a new vector, and a lot of times we'll call it that R vector, and that little symbol above it means the vector. So tip to tail geometrically represents addition. So subtraction we can think of as addition. So if we want to figure out what is the vector u plus v, then we think of that as being u plus the opposite of v. And the opposite of v means the same length but the opposite direction. I'm going to get a different color for that. So I'm going to call that vector right here, this vector is the negative of v. It's the exact opposite direction but the same length. Then I can move that negative v vector, got to use your imagination here, so that it goes tip to tail with the u vector, and so then that resultant, remember that's what we get when we add those together, so that vector, that red vector, is then u minus v. So when you add and subtract vectors, it follows what we refer to as the parallelogram rule. So if we create a parallelogram with two vectors, so I'm going to make one up here. I'm going to say here's a vector, and I'm going to call that vector p, and here's another vector, and I'm going to call that vector q. So these together can make a parallelogram. So when you put them where their tails are together, then you can visualize then a parallelogram. So the idea is if we slide that q up so that it goes along here, because remember these are slidable, then that is that one of the diagonals of this parallelogram is going to be the sum of those two vectors. So that is the vector p plus q. Now, if I look at the opposite of q, so I'm going to go the other direction there, and now that's going to be a negative q, and I'm going to then imagine, trying to figure out, nope, I've got it there already. So then what we can do is imagine that we are, I'm going to stick with the blue. So if I look at that vector negative q plus p, which is the same thing as p minus q, then that is going to be the other diagonal of that parallelogram. So that vector right there is the vector p minus q. So the idea being, if you draw a parallelogram using two sides of that parallelogram as vectors, then one of the diagonals is the resultant, the sum of those vectors, and the other diagonal is going to be the difference of the vectors. So let's look at the next screen here. And let's talk about multiples of a vector. So this is now we're talking about scalar multiples. So we can look at multiplying a vector v by some number. So if I multiply that v vector by 2, then what we get is something that points in the same direction as v, but is twice the length. And similarly, if we did something like a negative 3v, then that would be the opposite direction and 3 times the length. So that would be the vector negative 3v. Okay, so let's see if we can put this together a little bit with this diagram. We see here that we have a square, and ABCD is a square, and you can see the side length is 4. So see if we can answer these questions that refer back to this diagram using our kind of growing knowledge of vectors here. So we want to know what is the vector CD equal to. Now remember, this is a vector, so it wouldn't be correct to say that's equal to 4 because 4 is a scalar and CD is a vector. So what we're doing is, here's our vector CD right here, and so we want to find something that is equivalent to that. That is, what is another vector that is in the same direction and the same length? And that would be this vector over here that starts at B and goes to A. And so that would be the vector BA. See what we're saying there? Now, number 2 is asking for the magnitude of vector BC. So now you can see vector BC is going here, and this means the magnitude, which is the length. And since this is a square, all the sides are the same length, that makes the magnitude of BC equal to 4. So next we're going to talk about the magnitude of vector AB plus BC. So first we have to add vector AB to vector BC. So let's see, here's vector AB, and there is vector BC. Those are tip to tail, so the resultant is going to be this vector right there. That's our vector that is AB plus BC. And now the magnitude of that vector means we want its length. And so now what you can do is think about that right triangle that you have created that's got 4 for a side length. And since that's isosceles, if you think back to your geometry days, then that's going to be 4 square root of 2, or you can real quick do a Pythagorean theorem argument. Now, different than in number 4 is we want the magnitude of AB, which we know is 4, plus the magnitude of BC, which is also 4, is going to make that be equal to 8. Now, the next one is kind of curious. So we are going to add all these vectors together. Now, follow me here as I go through this. So we're going to go vector AB plus vector BC plus vector CD plus vector DA takes us all the way back to where we started. So this is the sum of a bunch of vectors. We're going to get a vector that is actually just that point. That is known as the 0 vector. Okay, so a 0 vector has length 0, magnitude 0, in any direction that you like. Okay, let's see if we can do AD minus AB. And I'm running out of colors here, so I think I'll go back to red. So here is our vector AD right here, and AB is right here, but if we go, the negative of that is going to change the direction and go this way. So this is vector AD, and we're going to add to that the negative of vector AB, which is BA. So I'm going to imagine sliding that down over here. So here is the AD, and then minus AB is going to go there. We're talking about this vector right there, which looks like it's going to be right there if I slide it up to where it fits in that square, and that goes from B to D, so that is the vector BD. Very good. Hopefully this will help you with homework number 7.